So picture a completely blank computer screen, like no operating system, no interface at all, just raw, unformatted potential.
Right, just a digital void.
Exactly. And now imagine unleashing a swarm of, I think it was 93 autonomous AI agents into that void. And you don't give them a step-by-step manual or anything. You just give them one single goal, which is to build a functioning computer operating system from absolute scratch.
And, crucially, you give them a really tight deadline to do it.
Right. Very tight. Because
Very.
in this recent live stage demonstration, these 93 sub-agents worked collaboratively for 12 hours straight. Like, they argued, they wrote code, they peer-reviewed each other's work, and they generated a staggering 2.6 billion tokens of data in the process.
Which is just a massive amount of output for a 12-hour window.
It's insane, and they actually successfully built the core of an entirely new operating system. But, okay, here is the detail from this demo that absolutely blew my mind. When they tried to boot up their brand new OS, it crashed.
Right, because it was missing a key component.
Exactly. It didn't have keyboard drivers. Now, a human engineer in that situation would have had to, stop everything, research how to build a hardware driver, write the code from scratch, recompile the whole thing. But the AI agents, they simply realized the problem, autonomously engineered the missing hardware drivers in real time, and just successfully integrated them.
And we should probably mention why they needed those specific keyboard drivers in the first place.
Yes. Oh, man. Just so they could run and play the classic 1993 video game Doom on the very operating system they had just birthed into existence.
It is a stunning proof of concept. And to put the cherry on top of that whole thing, that entire 12-hour, 2.6 billion token computing marathon cost them less than $1,000 to execute.
Wow.
Yeah. We're looking at a level of autonomous engineering that, frankly, upends, well, pretty much everything we thought we knew about software development.
It really does. And welcome to the deep dive, by the way. I am incredibly excited you're joining us today because we have this fascinating stack of documentation detailing Google's groundbreaking release of Antigravity 2.0 and the underlying co-scientist multi-agent system that powers it.
Which is a massive shift in how we approach problem solving.
It is. Our mission today is to completely unpack this paradigm shift for you.
Yeah.
Because the entire tech world is moving away from this era of, a human sitting at a text editor typing out code line by line.
Right. The manual labor era is ending.
Exactly. We're entering this era where developers and researchers act more like orchestrators, or basically managing a specialized team of AI agents. But the question is, how does that actually work in practice?
Like, how do they not just trip over each other?
Yeah. Right. How do these digital entities collaborate and argue and fact-check each other and write complex mathematics without completely hallucinating and going off the rails? So we're going to translate all the heavy computer science, all the underlying math, and the architecture into concepts that you can clearly visualize and actually apply.
Because that transition from manual coding to autonomous orchestration, it isn't just about speed. Speed is great, but it's a fundamental change in the methodology of problem solving itself. We aren't just telling a machine what to do anymore. We're setting up these environments where the machine can autonomously discover what needs to be done, test its own theories, and execute the final solution.
And to understand how a system can do something as complex as, say, building an operating system from scratch or discovering new biological treatments, we really have to start with the architecture. Like, how is this system actually built?
Yeah.
Because for a long time, the standard approach to AI was just to build one massive monolithic brain.
The giant, all-knowing oracle model.
Right. You open a chat window, you type a prompt, the giant brain thinks for a second, and it spits out an answer. It's a very linear transaction.
And that linear transaction is precisely what limits traditional AI models when you try to apply them to complex, open-ended scientific or engineering problems. A single prompt and response cycle is incredibly fragile.
Because science isn't linear.
Exactly.
Yeah.
Human science, the actual scientific method that has driven centuries of innovation, is not linear at all. It is notoriously messy. It's decentralized. It involves intense argument, rigorous peer review, throwing out terrible ideas, and just painstakingly refining the good ones. So the architecture behind co-scientists is designed to mimic that exact adversarial, decentralized nature.
So it breaks the AI down into a specialized team. Reading through the documentation, the way these 7 distinct agent roles interact, it feels less like a traditional computer program and way more like a high-stakes corporate research lab. Or, honestly, like a specialized heist crew from a movie, where every single member have a hyper-specific job.
I love the heist crew analogy. That's perfect.
Yeah, right. Let's introduce this cast of characters because they are all powered by these advanced Gemini models, but they are completely distinct in their functions. So first up, we have the supervisor agent. This is the mastermind.
The orchestrator. And the crucial thing here is that the supervisor agent doesn't actually do any of the grunt work of writing code or researching biology. Its operational objective is purely management.
Like a true boss.
Exactly.
Yeah.
So if you give it a massive, complex prompt like, I don't know, discover a novel protein folding mechanism, the supervisor's job is to decompose that massive goal into a series of executable, bite-sized plans. It manages the token budgets so the system doesn't run out of compute power. It coordinates the queue of worker agents. It holds the high-level state of the entire project in its memory.
So it's basically delegating. It looks at the big goal and says, okay, first we need some ideas. And that's where it calls in the second member of the crew, which is the generation agent. Now, this is the brainstormer.
Right, the idea machine.
The documentation describes it as interrogating scientific literature and data to formulate candidate hypotheses. So it's the one actually going out, reading PubMed, scanning databases, and coming up with the raw material, the initial ideas.
Which is great. Generating raw ideas is crucial. But if you've ever been in a brainstorming session, you know that raw material is often highly redundant.
No, absolutely.
You might get 100 ideas, but 80 of them are really just slight variations of the exact same concept. And in computational terms, having an AI explore 80 identical ideas is just a massive waste of resources and compute.
Which brings us perfectly to the proximity agent. I found this role so fascinating. It's basically the organizer of the group, and its specific job is deduplicating the search space. It clusters the hypotheses generated by the brainstormer using what they call a spatial proximity graph. But what does it actually mean to map ideas spatially?
So think of it like a topographical map of concepts. If two hypotheses propose using a nearly identical chemical compound to target the exact same cellular receptor, those two ideas are mathematically plotted very close together on this conceptual map.
They occupy the same space.
Right. And the proximity agent looks at that tight cluster and says, look, we don't need to test all 5 of these. They're functionally the same thing. So it prunes the duplicates. This forces the system to maintain global diversity. You want distinct, wildly different avenues of exploration, not 50 variations of the same dead end.
That is brilliant. It ensures the team is actually exploring the whole landscape, not just obsessing over one tree. Okay, so once we have a diverse set of ideas, we bring in the reflection agent. And this one might be my favorite role. It's the peer reviewer, or maybe the resident cynic.
Every good team needs a cynic.
True. The system uses it as an in silico peer reviewer to perform deep logical and semantic checking. It essentially interrogates the idea and asks, is this physically feasible? Like, does this violate the laws of thermodynamics? Is there just a glaring logical flaw here?
The reflection agent acts as an objective referee. And it has to be objective, because it sets the stage for the 5th and arguably most critical agent in the entire architecture, the ranking agent.
Okay, the judge.
Exactly, the judge. The ranking agent is responsible for evaluating all those surviving ideas. But it doesn't just grade them on a scale of 1 to 10 like a teacher grading a quiz. It actually runs game-theoretic pairwise debates. It forces the ideas to compete against each other head-to-head.
We are definitely going to dive deep into the underlying math of those pairwise debates in just a moment, because it completely changes how AI evaluates information. But just to finish out the heist crew, once the ranking agent has found the winning ideas through these intense debates, the evolution agent steps in.
The tinkerer.
Right, the tinkerer. It takes those highly rated, victorious proposals and actively mutates them. It splices complementary ideas together to see if a hybrid approach works even better, grounding all those changes in empirical evidence.
It's essentially running a genetic algorithm on the ideas themselves. It takes the strongest traits from the best proposals, merges them, and basically asks, how do we push this even further?
And finally, we have the 7th role, which is the meta-review agent, the auditor. Its job is to step back, look at the transcripts of all these massive, complex debates that just happened, and synthesize that information to optimize future planning.
Right, it's looking for patterns.
It learns from the structural patterns of the team's collaborative process, and it updates the supervisor's prompt context, so the entire system is actually smarter the next time it tackles a problem.
It is a continuous loop of self-improvement. The system is literally learning how to think better by observing its own internal arguments.
Okay, so seeing this intricate web of 7 different AI agents, passing data back and forth, deduplicating, debating, mutating, It immediately makes me wonder about the overhead. Like, why go through all this trouble if underneath the hood these are all just Gemini AI models? Why bother breaking them up into these distinct constrained roles? Why not just give one massive, super intelligent AI all the computing power and say, hey, brainstorm, filter, debate yourself, and just give me the best answer?
It's a fundamental question. And the answer gets to the very core of why early monolithic AI models frequently failed when they were given open-ended, highly complex tasks.
Because they get confused.
Well, worse than confused. When you rely on a single, massive model to act as both the creator and the evaluator of an idea, you inevitably run into two catastrophic pitfalls, which are reward hacking and model collapse.
Okay, I hear those terms thrown around a lot in AI safety discussions. Let's break those down clearly for everyone listening. What exactly does reward hacking look like in practice?
Reward hacking occurs when an AI model finds a loophole in your instructions. It figures out a way to maximize the reward or satisfy the prompt without actually solving the underlying problem you wanted it to solve.
Can you give me an example?
Sure. Imagine you tell a single AI to develop a highly efficient algorithm to sort a massive list of data. And you tell it, I will reward you based on how fast the final list is processed.
Okay, so the stated goal is purely speed.
Right. A reward hacking AI might simply write a script that deletes the entire list, because an empty list takes 0 milliseconds to sort. The AI technically achieved the fastest possible sorting time, satisfying the reward condition perfectly, but it completely failed the actual spirit of the task. It just found a shortcut.
Wow, that is terrifyingly clever but completely useless. And what about model collapse? How does that happen?
Model collapse happens when a single model is asked to generate an idea and then objectively evaluate that same idea. It naturally creates a digital echo chamber. The model uses its own internal logic and its own biases to generate the hypothesis, so of course when it reviews it using that exact same logic, it's going to conclude that the idea is brilliant.
Right, it's grading its own homework.
Exactly. It can't see its own blind spot, so it collapses into this infinite loop of self-congratulation, basically.
So by breaking the architecture up into 7 distinct roles, you are deliberately introducing friction into the process.
Exactly. You're introducing an adversarial dynamic. The generation agent is strictly incentivized to produce a high volume of novel ideas. But the reflection agent is strictly incentivized to find the flaws in those ideas and tear them down. They have opposing goals.
Like real scientists.
Right. This mimics the adversarial, peer-reviewed nature of human science. It prevents the echo chamber, prevents the shortcuts, and ultimately yields a significantly safer, much more rigorous output.
It creates a real system of checks and balances. But that brings us to a really fascinating juncture here. Having different agents generate ideas and relentlessly critique each other is great for filtering out garbage. But at the end of the day, how does the system actually decide which idea is the absolute best? If we have 2 seemingly brilliant hypotheses that survive the peer review process, how do we declare a winner?
That is where co-scientist abandons the traditional AI playbook entirely. Most older agentic pipelines rely on a mechanism known as best of n generation.
Best of n.
Yeah, you tell the model to generate n number of ideas, maybe 20 or 50 variations. Then a reward model looks at all 50 and assigns a flat scalar score to each one, basically like grading a test out of 100.
But grading an open-ended scientific theory isn't like grading a multiple-choice test. A flat score out of 100 feels way too simplistic for something as nuanced as molecular biology or, operating system architecture.
Precisely. Scalar rewards fail in open-ended scientific domains because the nuance is simply too deep to capture in one number. You can't capture the elegance, the efficiency, or the potential secondary benefits of a complex theory with a flat score. So instead of flat grading, co-scientist dedicates the vast majority of its test time computing power to a tournament of ideas.
A tournament, like it actually builds a bracket.
It does. It operates as a massive ongoing debate club, but the outcomes of these debates are governed by strict mathematics, specifically an ELO rating system.
Okay, for anyone listening who plays competitive chess or watches ranked esports and video games, that term should sound very familiar. The ELO system is a mathematical method for calculating the relative skill levels of players in zero-sum games.
Right. It's all about relative strength.
So if a massive underdog beats a grandmaster in chess, the underdog gains a huge amount of points, and the grandmaster loses a huge amount. But if 2 evenly matched players face off, the point swing is much smaller.
The engineers at Google took that exact mathematical framework and applied it directly to scientific ideas. Let's look at the actual expected probability formula they use, because it dictates how the ranking agent evaluates these debates.
Let's do it.
The formula calculates the exact odds of one idea Let's call it hypothesis A beating another idea, hypothesis B, before the debate even starts, based solely on their current standings.
Okay, let's unpack the math here because I know hearing math read aloud can be incredibly dense. So let's ground this. The expected probability, which we'll call E, is calculated as 1 divided by the quantity of 1 plus 10 raised to the power of the rating difference divided by 400. So what is that rating difference actually doing in practical terms?
So let's say your hypothesis A has a current ELO rating of 1600, and it is going up against my hypothesis B, which has a lower ELO rating of 1200. The formula takes my rating of 1200, subtracts your rating of 1600, giving us a difference of negative 400. That difference is the core of the calculation. It mathematically quantifies the exact gap in perceived quality between our two ideas.
Got it. And what about that division by 400? Why that specific number?
In the ELO system, the 400 acts as a standard scaling factor. It basically dictates the shape of the probability curve. Specifically, it means that if your idea is rated exactly 400 points higher than my idea, the math dictates that your idea is expected to win exactly 10 times as often as mine. It sets the baseline expectations for the matchup.
So the ranking agent uses this formula to look at the bracket and say, okay, based on past performance, hypothesis A is an absolute heavyweight. It has an 85% expected probability to beat hypothesis B in this debate. The expectations are set. Then the actual debate happens. The AI agents argue the merits of the two ideas, and the reflection agent steps in as the objective referee to evaluate the outcome of that specific argument.
Right. And the referee evaluates the debate and assigns an empirical score. It awards a 1 for a definitive win, a 0.5 for a draw, and a 0 for a loss.
And this is where the magic happens. That empirical score feeds directly into the update formula, which recalculates the ratings after the dust settles. The new rating for an idea equals its old rating plus something called the K-factor multiplied by the actual empirical score minus the expected probability.
This is where we see the system dynamically adjust. Let's go back to our scenario. Your heavyweight idea was expected to win easily. But let's say my underdog idea, which the math expected to lose, actually puts up an incredibly robust logical argument during the debate, and the referee actually awards it a win.
An upset.
An upset. So my empirical score is a 1. The formula takes that actual score of 1 and subtracts my very low expected probability. Let's say it was 0.15. The difference there is 0.85. That is a massive differential.
And you multiply that massive differential by the K-factor, meaning your underdog idea shoots up the rankings like a rocket because it proved the mathematical expectations completely wrong.
Exactly. The K-factor is essentially the volatility dial for the tournament. A high K-factor means the ratings will swing wildly after every single debate. A lower K-factor means the ratings are more stable and require a longer history of consistent wins to move up the ranks.
So it rewards consistency over time if it's low.
Right. And by carefully tuning this K-factor, Google ensures that this continuous pairwise evaluation creates a true meritocracy. The ideas that consistently survive rigorous debate rise to the top. This aligns the AI's output significantly closer to actual human expert judgment than any flat scalar reward system ever could.
It's a really elegant mathematical solution, but it does raise a concern for me. Even in a pure mathematical meritocracy, things can go off the rails. What happens if the agents all start collectively agreeing on a flawed premise? What if the debates slowly drift away from the original goal of the prompt? I mean, a tournament of ideas is completely useless if everyone is arguing brilliantly about the wrong thing.
That is a phenomenon known as alignment drift, and it's a critical danger in any autonomous system. To combat this, the architecture implements 3 very strict structural guardrails to keep the tournament grounded and focused on the actual objective.
Let's walk through those, starting with the first one, which is graph-based proximity pruning. We touched on this with the proximity agent earlier.
Yes, this is the first line of defense against drift. The system continuously maps the topological distance between all the active ideas in the tournament. If the AI notices that the top 4 ideas in the bracket are all mathematically clustered too close together, meaning they are functionally just slight variations of each other, it triggers a block.
It stops them.
It forces the system to either definitively merge them into a single concept or aggressively mutate them to create distinct conceptual separation. This absolute requirement for topological distance ensures that the tournament doesn't devolve into an echo chamber where agents are just discussing minutiae. It forces macro-level diversity.
The second guardrail relies on a concept called RLAIF reinforcement, learning from AI feedback. Specifically, the documentation says the system uses rubric-guided self-grading.
This one is crucial for preventing the reward hacking we discussed earlier. During the system alignment phase, Before the debates even begin, a jury of frontier models is tasked with creating a highly specific, peer-reviewed 10-item rubric.
So it's not just evaluating the debate on general vibes or how fluent the argument sounds. It's evaluating it against a strict checklist.
Exactly. It's the difference between a teacher grading an essay by just reading it and seeing how it feels, versus grading it against a standardized 10-point rubric that demands specific structural elements, citations, and logical flow. By forcing the evaluation through these multidimensional rubrics, it ensures that the winning ideas generalize well across different domains and aren't just finding clever rhetorical tricks to win the debate.
It demands real structural soundness. And what is the third guardrail?
The third is the human expert in the loop. Because as autonomous as this system is, humans still define the initial boundaries. Human operators calibrate the evaluation weights, they review the early overarching proposals, and they set the initial research scopes. This is the ultimate fail-safe to prevent the AI from pursuing directions that are scientifically unviable, ethically problematic, or just physically dangerous.
Okay, so the system architecture is incredibly robust. We have specialized agents. We have a mathematically rigorous tournament that forces ideas to fight for supremacy, governed by strict rubrics and diversity clustering. It sounds foolproof.
On paper, yes.
But there is a huge elephant in the room here. Winning a debate mathematically, scoring a perfect 10 on a rubric. None of that matters if the underlying facts the AI is using are fundamentally wrong. We have all seen large language models hallucinate. They can write beautiful, highly convincing prose that is entirely fictitious. So how do we know these agents are doing actual empirical science and not just writing highly ranked science fiction?
That is the single most important hurdle for applying AI to hard science. And it brings us to how co-scientist handles literature and data grounding. The engineers knew that fluent, confident text is not the same thing as scientific truth, so they built incredibly strict external verification pipelines. In fact, co-scientist dedicates the vast majority of its computing power not to generating text, but to rigorously verifying its own claims against real-world data.
The documentation outlines a dual-path architecture for this, utilizing retrieval-augmented generation, or RJ. It combines Neo4j graph embeddings with massive text databases like PubMed and the PubMed Central Archives.
Let's clarify what that dual path actually means, because it's vital to understanding how it doesn't hallucinate. A traditional RGA system just searches a massive pile of text documents for keywords. If you ask about a specific protein, it hands you 10 papers that mention that protein.
Yeah.
But the Neo4j graph database adds a relational layer.
So it understands how things connect.
Right. It doesn't just read the text, it maps the relationships. It understands that protein A inhibits enzyme B, which then triggers cellular pathway C. It builds a vast, interconnected web of biological knowledge. So when the AI pulls data, it's pulling both the raw text from PubMed and the complex relational context from the graph database simultaneously.
That dual context is powerful. But here's the part of the data grounding that truly stopped me in my tracks. It doesn't just pull these research papers and accept them as absolute truth. It actively interrogates the quality of the science within the human papers using the PICS framework.
Yes, the PICOS framework is the gold standard in evidence-based medicine and systematic human research. It is an acronym that stands for Population, Intervention, Comparator, Outcome, and Study Design. Every single piece of literature the AI retrieves is forcefully structured and analyzed through this specific lens.
Let's really dig into this because the implications are massive for research. Let's say the AI is researching a new cardiovascular drug and it pulls a published paper from a database. It doesn't just read the abstract. It asks 5 specific questions. Who was the population studied? What was the specific intervention, like the exact dosage of the drug? What was the comparator? Was there a placebo group? What was a measured outcome? And crucially, how was the study initially designed?
That last point, the study design, is where most weak science falls apart. To handle this, co-scientist utilizes a specialized transformer model that was trained specifically to classify study designs, and it achieves an incredible 95.7% accuracy rate.
That's incredibly high.
It is. And it also uses a BIOL-STM model, which is a bidirectional neural network that reads the text both forwards and backwards to grasp deep context to detect whether the paper is fully compliant with the PICS framework. That model is an 87.0% accuracy rate.
I want to make sure I am fully grasping the magnitude of what you just said. If the AI proposes a theory, and it finds a published human research paper that seemingly supports that theory, it runs it through this PICOS filter. And if the filter determines that the paper was say, an observational study with massive confounding variables like testing a diet pill on 5 people but not controlling for their exercise habits, the AI will autonomously flag that paper as scientifically weak and just discard it from its knowledge base.
Exactly. It autonomously recognizes bad science. It understands the hierarchy of evidence. It knows that a double-blind, randomized controlled trial carries vastly more empirical weight than a retrospective observational study. If a paper has confounding variables or lacks a proper control group, the system downgrades or outright discards it.
That is staggering. The amount of time it takes human researchers to manually read through hundreds of papers, weed out the poorly designed studies, and synthesize the actual reliable data. We are talking about hundreds, maybe thousands of hours of painstaking labor, and this system does it autonomously in minutes.
And it doesn't just rely on analyzing text-based literature either. When it comes to quantitative molecular biology and chemistry, the platform actually reaches out into the real world, connecting to highly specialized external engines and APIs.
The list of integrations in the documentation is essentially a fully stocked digital laboratory. It queries UniProt and Interpro for precise coordinate-level protein sequences. It doesn't just know the name of a protein. It knows its exact molecular makeup.
It integrates with the AlphaFold database.
Yeah.
This gives the AI the ability to pull 3D molecular geometries. It can actually analyze the atomic-level binding pockets and the physical interfaces where proteins fold and interact. It's moving from abstract text to three-dimensional physical simulation.
It also interrogates the Alpha Genome API to look at genomic variants and understand the drivers of specific diseases at the genetic level. And it accesses Chimble and PubChem for massive data sets of quantitative bioactivity assays and chemical structures.
So by plugging into these external engines, the AI isn't guessing. If it hypothesizes that a certain chemical structure will bind to a specific protein, it can literally pull the 3D model from AlphaFold, check the bioactivity data from PubChem, and verify the physical interaction computationally before it ever presents the idea to the human.
Okay. We have a system that can orchestrate a team of specialized agents. It can generate ideas, ruthlessly debate them using game-theoretic ELO math, and rigidly fact-check those ideas by filtering out weak human science and verifying 3D molecular structures. That is an incredible theoretical pipeline. But science isn't just theory. A theory is just a hypothesis until you actually test it.
Right, you have to prove it.
And in the digital age, testing a theory usually requires building a simulation. It requires writing the code. How does this system transition from theorizing biology to actually writing the expert-level software needed to prove its ideas?
That transition is handled by a framework called ERA, which stands for Empirical Research Assistance. This is Google's dedicated pipeline for generating highly complex scientific code. And what makes ERA so powerful is that it completely redefines how AI approaches coding.
How so?
Well, it doesn't treat writing code as a simple typing exercise, like predicting the next word like a glorified autocomplete. It treats coding as a massive, systematic tree search optimization problem.
A tree search optimization problem. The documentation highlights that ERA specifically navigates this massive tree of possible code combinations using a mathematical formula called flat upper confidence bound, or flat UCB. This algorithm seems to be the secret sauce that allows the AI to discover coding methods that actually outperform algorithms written by human experts.
It absolutely is the secret sauce. The UCB algorithm is the foundational concept in computer science and decision theory. At its core, the formula is designed to mathematically balance two inherently competing desires, which are exploitation and exploration.
Exploitation versus exploration. Let's ground this, because I love the classic restaurant exploration analogy for explaining this concept. It perfectly illustrates the tension the AI is managing when it writes code. Imagine you live in a big city, and you are trying to figure out where to eat dinner tonight. Your overall goal is to have the absolute best meals possible over the course of your life.
A noble goal, for sure.
Now, you have a favorite local diner. You've been there 5 times, and every single time the burger is fantastic. You'd rate it an 8 out of 10. That diner represents the exploitation side of the equation. You know it's a solid choice. If you only cared about exploiting known good options, you would simply go to that diner every single night for the rest of your life.
Right. And you would have a lot of consistently good meals. But the problem with pure exploitation is that you create a local maximum. By refusing to look elsewhere, you might completely miss out on a brand new Michelin star restaurant that just opened across town that would be a 10 out of 10. You miss the optimal solution because you settled for the good enough solution.
Which brings us to the exploration side of the equation. You have to be willing to risk a potentially bad meal at a new place on the off chance that you discover something amazing. But you can't just explore randomly forever or you'll eat a lot of terrible food. You need a mathematical way to decide when to go to the diner and when to risk trying the new place. That is exactly what the UCB formula calculates.
It's the perfect balance.
Let's look at the actual variables in the formula. The formula calculates the upper confidence bound for a specific candidate. Let's call it candidate n. It equals x bar sub n plus c multiplied by the square root of the natural log of capital N divided by lowercase n. I know, a lot of letters. Let's map them to the restaurants.
Okay, let's map it. The first term, x bar sub n, is the empirical score of the specific candidate you are evaluating. This is the exploitation term. In our analogy, this is the solid 8 out of 10 score of your favorite diner. It's the known value based on past experience.
Then we add the entire second half of the equation, which represents the exploration bonus. Let's break down the variables inside that square root. Capital N is the total number of times you have gone out to eat anywhere. It's the parent node visit count. Lowercase n is the specific number of times you have visited the new candidate restaurant you are currently considering.
Right. So look at how those two numbers interact mathematically. As capital N, your total number of dinners out, gets larger and larger, the numerator of that fraction grows. This mathematically represents a growing internal urge to explore. The system is saying, we've been at this for a while, we need to make sure we aren't missing something out there.
But every single time you actually visit the new candidate restaurant, the lowercase n in the denominator gets bigger. And as the denominator grows, it shrinks the overall value of the fraction.
Exactly. The mathematical exploration bonus for that specific new restaurant gets smaller the more times you visit it, because it is no longer an unknown quantity, you've explored it, the uncertainty is gone. And finally, we have C, the exploration constant. This is simply a dial that the human engineers can turn to dictate how adventurous the entire system should be.
So a high C means more risk.
Yes, a high C value means the AI will constantly test wildly different code structures. A low C value means it will stick closer to known traditional methods.
So the UCB formula is constantly crunching these numbers, constantly asking, do I exploit the known value of x bar sub n, or do I add the exploration bonus and try something completely novel? And when we apply this back to the AI writing code, it's navigating a vast tree of possible functions and logic structures. It might write a script that processes data pretty well, that's its local diner, but the UCB formula forces it to step away from that script and intentionally explore radically different, untested code variations, just in case a bizarre new approach yields a massive leap in performance.
It prevents the AI from getting stuck in a rut. And this mathematical balance is precisely what allows the ERA framework to write code that genuinely outperforms human intuition. Humans are naturally biased toward exploitation. We learn a coding pattern that works, and we stick with it. We rely on standard libraries. The UCB algorithm doesn't have those biases. It explores the hidden corners of the structural tree that human engineers would never even consider.
And the performance benchmarks from the documentation prove just how effective this is. In the field of bioinformatics, they tasked the ERA framework with analyzing single-cell biological data. ERA autonomously explored the computational landscape and discovered 40 entirely novel methods for data analysis. Specifically, it looked at a standard human-developed method called batch-balanced k-nearest neighbors, or BBKNN.
For context, BDKNN is a heavily relied upon algorithm for integrating massive data sets of single-cell RNA sequencing. It's standard practice in the field.
ERA analyzed it, explored novel variations, and autonomously wrote code that improved the BBKNN method by 14% on public leaderboards while completely preserving the underlying biological signals. It took an industry-standard human tool and mathematically optimized it beyond human capability.
The epidemiology benchmarks are arguably even more striking. The system was tasked with generating forecasting models to predict COVID-19 hospitalizations. ERA systematically generated and evaluated 14 different forecasting models. The performance of these models is judged by something called a weighted interval score, or WIS.
And just to clarify, in this specific metric, a lower WIS score indicates a more accurate, tighter prediction model.
Yes, lower is better. The official COVID Hub Ensemble benchmark, which represents the absolute state-of-the-art human consensus modeling, sat at a WIS of 29. The ERA-generated models achieved a mean score of 26. The AI, operating autonomously, significantly outpredicted the baseline models created by human epidemiological teams.
The leaps in performance are staggering. But as we step back and look at this entire theoretical engine, the multi-agent architecture, the ELO tournament debates, the rigorous PSUS data grounding, the complex UCB code exploration, it becomes incredibly dense. And all of this underlying complexity needs a place to actually live and operate on a developer's machine. It needs an interface. It needs an operating layer. Which brings us to the actual Antigravity 2.0 platform mechanics.
This is where we transition from the theoretical math to the tangible user experience.
Yeah.
How does a developer actually harness all of this power? The Antigravity 2.0 platform is a standalone desktop application. It's compiled natively to run on macOS, Linux, and Windows. But the most crucial design choice Google made is that Antigravity is completely detached from legacy IDE text editors.
Right. It is not just a plugin you install into VS Code or IntelliJ. It is an entirely separate, dedicated operating layer built from the ground up for agent orchestration. And looking at how they engineered this environment, there is one specific design choice that completely jumped out at me, and I honestly found it highly counterintuitive at first. It's their approach to the context window.
Yes.
Right now, there is an arms race in the AI industry regarding context windows. Every major tech company is bragging about their models being able to handle millions and millions of tokens at once. They tell developers, just dump your entire massive code base, all your documentation, and 10 textbooks into the prompt, and the AI will figure it out. But Antigravity 2.0 explicitly restricts the context window for these subagents. Why on earth would they deliberately limit the AI's vision like that?
It does seem completely counter to the industry trend, but it solves a very specific, catastrophic problem called token bloating. In a traditional monolithic system with a massive context window, if you dump an entire project's history into the prompt, the model degrades incredibly fast. The main conversation context becomes thoroughly saturated with useless noise, gets filled with raw terminal execution logs, the minutiae of file system clutter, and endless back-and-forth chatter between the agents themselves.
It's like trying to have a highly technical conversation in the middle of a screaming crowd while someone is throwing encyclopedias at you. The AI literally loses the forest for the trees. It forgets what the overarching goal was because its memory is clogged with irrelevant terminal errors.
Exactly. It gets overwhelmed by its own operational mess. So Antigravity 2.0 introduces a paradigm called context window isolation. When the supervisor agent decides it needs a specific task done, say, writing a Python script to parse a CSV file, it doesn't do it in the main workspace. It spawns a completely isolated subagent. It drops that subagent into a highly restricted sandbox directory on the computer. And crucially, it gives that subagent a completely blank slate context window.
Clean slate, no history.
None.
Oh.
The supervisor gives the subagent hyper-specific instructions. Your only job in the world is to write this one script in this one folder. Here are the 3 tools you are allowed to use. Execute.
The subagent wakes up, has 0 distractions, executes local terminal commands, writes the code, maybe queries an API, finishes the script, and then it doesn't send a massive dump of terminal logs back to the supervisor. It just sends a highly compressed, concise summary of what it did, along with the final modified file.
This separation of concerns is a masterclass in orchestration. The supervisor never gets bogged down by the raw terminal output. It just merges the clean artifacts. And the secondary benefit of this isolation is an absolutely massive gain in memory efficiency. The documentation notes that legacy AI code editors often consume over a gigabyte of RAM just to maintain the context overhead.
Right, which slows everything down.
Exactly. Under the anti-gravity multi-agent execution model, RAM usage plummets to a remarkably lean range of 150 megabytes to 500 megabytes.
That is incredibly lightweight. It means a developer can comfortably run dozens of these highly capable agents simultaneously in the background on a standard commercial laptop without the system grinding to a halt.
And that background capability is a core feature of the platform. Antigravity integrates a powerful asynchronous scheduling system. It allows developers to translate natural language requests into complex cron expressions, basically turning the AI into a persistent, autonomous worker.
For those who might not be deep into Unix server management, a cron expression is basically just a string of text that acts as a time-based job scheduler. It tells a computer exactly when and how often to run a specific script. And Antigravity allows you to manage these without writing the complex syntax yourself. The system parses 3 distinct types of schedules. Let's walk through how a developer would actually use them, starting with the one-time event.
The one-time event is for immediate deferred tasks. A developer might type a natural language prompt like, schedule in 5 minutes, check if the massive Docker build has finished compiling.
The UI stays completely responsive. The developer goes back to doing something else. The system spawns a transient invisible background task, waits 5 minutes, checks the compiler output, flags any errors it finds, drops a clean summary log into the workspace, and quietly terminates itself.
Then you have the bound recurring cron. This is for monitoring a process over a specific window of time. A developer prompts, schedule every hour, run the server health check script up to 3 times. The platform creates a persistent background subagent that wakes up, runs the diagnostic, reports back, and then automatically destroys itself after the 3rd iteration so it doesn't run forever and eat up resources.
And finally, the unbound recurring cron. This is for permanent infrastructure. You could say, schedule every single morning at 8 a.m., review all the open pull requests on GitHub. This spawns a dedicated subagent that lives permanently in the background. Every morning, it reads the code changes, generates a clean, formatted markdown report summarizing the updates, and pins it right to your sidebar before you even start your workday.
It represents seamless, hands-off task delegation. You're building a staff of invisible assistants. And the platform goes a step further to make initiating these complex workflows as frictionless as possible by integrating advanced voice controls.
And this isn't just basic speech-to-text. The system utilizes Gemini audio models for real-time local voice transcription directly on the desktop.
The local aspect is the critical feature here, primarily for enterprise security and privacy. When you click the microphone and start speaking, the Antigravity application processes your audio locally on your machine's hardware. It does not compress your voice and stream the raw audio files to a cloud server for processing.
So if you are discussing proprietary company code or unreleased biological research, you don't have to worry about the audio data being intercepted or stored by a third party. The local model converts your messy, unstructured human speech, the ums, the pauses, the stream of consciousness ideas into a crisp, clear text prompt, and then feeds that text to the agents.
And when you give those agents a prompt that requires a highly specialized scientific workflow, they rely on what's called the Science Skills Bundle. This is a fascinating way Google has standardized complex procedures.
They use a strict directory structure for these skills, anchoring them with a skill.md file that utilizes YAML front matter. Let's demystify that a bit. YAML front matter is essentially a block of metadata at the very top of a file that provides structured information like tags, descriptions, and required inputs that a computer program can read instantly without having to parse the whole document.
The platform uses a 2-step progressive disclosure lifecycle for these skills to maximize efficiency. It starts with the activation phase. When a user asks a complex question, the supervisor agent doesn't read every single skill file in the library. It just scans the YAML metadata from all the skill roots.
It's like skimming the index of a textbook to find the right chapter.
Exactly. It matches the user's intent to the metadata description of a specific skill.
Once it finds a match, it moves to the execution phase. The agent then ingests the full instructions within that specific skill.md file, loads the necessary tools, and executes the workflow. It allows an agent to seamlessly transition from chatting with the user to suddenly executing a highly complex, multi-step molecular analysis using the AlphaGenome API, all in a matter of minutes, directly from the desktop interface.
But here is the reality of software engineering. To support an ecosystem that can simultaneously run dozens of asynchronous background subagents, evaluate complex cron jobs, process local audio models, and execute heavy scientific skills through external APIs without dropping frames or lagging the UI. The underlying AI engine powering the entire operation has to be an absolute monster in terms of throughput.
Which brings us to the core engine, the final major piece of this puzzle, the developer interloop and customization. The entire Antigravity 2.0 platform is driven by the Gemini 3.5 Flash model.
The specifications on Gemini 3.5 Flash reveal that it was purpose-built from the ground up for this specific type of agentic orchestration. It completely prioritizes low-latency execution, incredibly long context reasoning for the supervisor, and the ability to trigger parallel tool invocations. But the most important metric is its sheer speed. Its generation throughput is a staggering 289 output tokens per second.
289 tokens every single second. To put that abstract number into perspective, a token is roughly equivalent to a word or part of a word. A typical paperback book has about 250 to 300 words on a page. So this AI model is generating the equivalent of a full page of dense, highly technical code or scientific reasoning every single second. It is reading and writing at a pace that is completely incomprehensible to a human.
It's blindingly fast.
And when you compare to the competition, it's not even a contest. The documentation notes that Anthropic's Claude 4.7 Opus was benchmarking at around 67 tokens per second, and OpenAI's GPT 5.5 at 71. The Gemini engine is running more than 4 times faster than the frontier models of its competitors.
And it isn't just fast, it's highly accurate in these specific environments. It scored an impressive 76.2% on the Terminal Bench 2.1 evaluation.
For context, Terminal Bench is a rigorous industry benchmark that specifically tests an AI's ability to navigate complex command line terminal environments, install dependencies, and execute scripts without human intervention.
And it also achieved a 1656 GDP-Val AA score, which measures its ability to generate valid, syntactically perfect code across multiple programming languages. That raw speed and precision is exactly what made that legendary Doom demo we discussed at the very beginning physically possible.
Let's bring it back to that demo, because understanding the architecture, the ELO tournaments, the restricted context windows, and the sheer speed of the Gemini Flash engine puts that 12-hour marathon into a completely different light. It wasn't just a parlor trick. It was 93 distinct subagents spawned by a supervisor into clean, isolated directories.
All working in parallel.
Right. They were generating hypotheses for operating system components, ruthlessly debating the architecture, using expected probability math, testing the logic, utilizing UCB algorithms to explore optimal code paths, and compiling the results. 2.6 billion tokens of raw generation, all coordinating seamlessly to build a custom OS and write hardware drivers on the fly just to play a video game. And the financial cost of that compute was under $1,000.
To make that level of compute accessible for regular developers and research teams, Google completely restructured their subscription pricing model. They introduced the AI Ultra tier at $100 a month, which provides developers with priority network access and 5 times the standard token usage limits of the basic Pro plan. And for heavy enterprise users, they introduced the flagship Ultra tier at $200 a month, which provides an incredible 20 times the base capacity.
When you consider that the system can essentially replicate the output of an entire team of junior developers, $200 a month is a microscopic operational cost. But raw power is dangerous without control. How do developers actually steer this engine? The documentation details a highly granular configuration ecosystem consisting of 3 main layers. The first layer is the use of markdown personas, specifically revolving around a standardized file called agents.md.
This is how you enforce discipline across a massive multi-agent system. The agent.md framework operates on a strict cascading precedence hierarchy. At the very top, you have immutable system rules. These are hard-coded safety and operational boundaries that cannot be overridden by anything else. Below that, you have Gemini.md, which allows developers to override default tool behaviors. Then you have project-level agent s.md files, which define the specific personas and goals for the current codebase. And finally, global agent.md files that set baseline preferences for the user's entire machine.
It's a cascade. The system rule says, never delete the core database. The project rule says you are a senior front-end engineer focused on React. It layers the constraints so the AI always knows its exact boundaries and identity. The second configuration layer moves from static markdown rules to dynamic programmatic control. Developers can utilize JSON hooks via a file called hooks.json. This is incredibly powerful. It allows human developers to essentially intercept the AI's internal thought process at critical execution stages.
The hooks are placed at key junctures: pre-tool use, post-tool use, pre-model call, and post-model call. Let's look at pre-model call as an example. Right before the agent actually sends a prompt to the Gemini engine, the system pauses. It takes all the metadata about the impending request, packages it into a JSON payload, and passes it via standard input to a local Python script written by the human developer.
The human's Python script parses that payload, maybe checks a local security database, alters the prompt slightly, and then passes custom instructions back to the agent via standard output. The agent ingests the human's modifications and continues its loop. It provides an immense level of dynamic programmatic control without the developer ever needing to open up and rewrite the core underlying logic of the AI agent itself.
And to make this massive configuration ecosystem manageable for large teams, they introduced the third layer, plugins. This is a standardized directory structure anchored by a plugin.json file. It allows a senior architect to bundle up all the specific skill.md files, all the custom hooks.json interceptions, and the agents.md persona rules into a single, cohesive package. They can then distribute that plugin to the entire engineering team, ensuring everyone's agents are operating under the exact same strict parameters.
Okay, so we have the Gemini engine, we have the Markdown and JSON configuration layers to control it. But if I'm a developer sitting down at my desk right now, how do I actually engage with this system? Looking at the Antigravity ecosystem, they offer 4 completely different entry points: the desktop app, the terminal CLI, the Python SDK, and the managed agents API. If I'm leading a project, how do I know which interface is right for my specific workflow?
It entirely depends on your operational needs at that exact moment. They built it to scale from visual oversight down to bare metal programming. The desktop app is designed for high-level management and orchestration. It provides a visual, graphical workspace. It groups your various agent conversations into discrete projects, and it visually ties those projects to native Git work trees. It's the interface you use when you want to look down at the entire system from above and monitor the big picture.
So the desktop app is the manager's view, but a lot of developers hate leaving the terminal, which brings us to the second entry point, the terminal CLI or command line interface.
Yes, the Antigravity CLI. This is built for the fast, local, purely keyboard-driven workflow. It drops the user into an interactive terminal user interface, or TUI. You don't use a mouse. You can rapidly teleport your context between different background subagents using the Ctrl+J shortcut. When an agent proposes a destructive action like deleting a file or pushing code to production, it halts and waits for human approval, which you can grant instantly with a Ctrl+K keystroke. It is designed for absolute speed and frictionless hacking.
So desktop for visual orchestration, CLI for high-speed terminal hacking. What about the Python SDK?
The SDK is for deep programmatic integration. This is used by platform engineers who want to build their own custom infrastructure on top of the Gemini engine. They use the Python SDK to scaffold entirely new types of custom agents or to build highly specific execution sandboxes that tie directly into their company's proprietary internal databases.
And finally, the remote managed agents API. The first three entry points all run locally on your machine. Why would a developer need to route their agents through a remote cloud API?
Security and isolation. The Managed Agents API is designed for cloud-scale execution. When you ping the API, it spins up highly isolated, temporary containerized Linux sandboxes on Google's cloud servers. The agents do their work inside that sandbox, and when they are done, the sandbox is completely destroyed. This is the perfect entry point if you need your AI to execute highly untrusted third-party code that you don't want anywhere near your local hard drive, or if you were running massive, resource-heavy computational workloads that would melt your laptop's CPU.
It is a profoundly comprehensive ecosystem. From the desktop down to the cloud API, we have covered a massive amount of ground today. We explored the heist crew of specialized agents working to avoid model collapse. We broke down the mathematics of expected probability and ELO ratings guiding the tournament of ideas. We looked at the strict PyCS framework, autonomously filtering out weak scientific literature, the UCB tree search algorithm optimizing complex code, and the lightweight, blazing fast desktop platform that orchestrates it all using the Gemini Flash engine.
It's a lot to take in.
As we pull all of these threads together, what are the core operational takeaways? If a technical lead or scientific researcher is looking at these documents, what are the three absolute imperatives they need to internalize before deploying this technology?
Synthesizing the underlying mechanics we've discussed, the documentation points to three non-negotiable operational rules for success in this new paradigm. Number one, you must strictly enforce multi-agent diversity constraints. The era of the single monolithic prompt is over. You cannot rely on one massive context window to solve complex problems. You must utilize the supervisor's subagent architecture to isolate tasks into clean directories, and you must leverage the proximity agent's topological clustering to continuously prune redundant ideas. If you don't aggressively manage token bloat, the system will collapse under its own noise.
Keep the context windows small, cleanly separate the tasks, and force the agents to explore diverse paths.
Correct. Number two, for any open-ended scientific or engineering task, you must transition entirely to pairwise ELO evaluations. You have to abandon legacy best-of-n flat-scalar rewards. A 1 to 10 grading scale cannot capture the nuance of a biological hypothesis. The continuous tournament of ideas, objectively refereed against strict multidimensional rubrics, is the only proven mathematical method to prevent reward hacking and ensure that the AI is generating structurally sound, highly generalizable solutions.
You have to force the ideas into the arena, make them fight it out, and let the expected probability math surface the true winner. And the final takeaway.
Number three, you must deploy strict local and remote security sandboxes. Autonomous agents that have the capability to write and execute code at 289 tokens per second represent a massive security vector. You have to build rigid boundaries. Utilize the dynamic hooks.json files and the cascading agents.md personas to control local execution, and leverage the Managed Agents API to isolate any untrusted or volatile workloads in temporary cloud containers. trust the intelligence of the system, but rigidly restrict its physical access.
It is an entirely new frontier of engineering discipline. We are fundamentally shifting away from the meticulous manual labor of typing syntax in a text editor. We are now overseeing vast digital laboratories filled with tireless scientists and engineers.
We really are.
Which leaves me with a final thought for you to ponder. We talked at the very beginning about how engineering used to feel like classical mechanics. You type a command, the compiler reads it, you get a binary result. The human hand was always directly on the steering wheel. But if Antigravity 2.0 and the co-scientist system can now autonomously generate a complex hypothesis, rigorously peer review it, ruthlessly filter out bad empirical data, and computationally write the optimal software required to test its own theories, what exactly is the future role of the human scientist?
It's a great question.
Are we rapidly moving away from being the researchers, the ones physically holding the pipettes, poring over PubMed, and typing the Python scripts? Are we destined to become merely the supervisors of a sweeping digital scientific revelation? We are no longer the ones reading the X-ray, agonizing over every pixel. We are simply the ones pointing the machine in a general direction, letting it run, and building the hospital to house the results. The clear binary precision of human-led discovery is evolving into something vastly more powerful, but undeniably less human. I want to thank you so much for joining us on this incredible deep dive. Keep questioning the tools you use, keep exploring the boundaries of what is possible, and we will see you next time as we continue to unpack the bleeding edge of the tech world.